technology. The story of molten salt reactors starts in the United States around the 1940s. There were two experiments performed, first in 1954 with the aircraft reactor experiment, which ran at 2.5 megawatt thermal power, followed by the molten salt reactor experiment that ran successfully for 4 years at 7.4 megawatt thermal power with a fluoride salt. And from this experiment, there was a lot of knowledge gained. Unfortunately, this research was stopped shortly after for political reasons. There were more investments that went to liquid metal-cooled reactors. And it's not before the beginning of this century, with the impulse of the Generation 4 International Forum, that molten salt reactors got attention again. The Generation 4 International Forum selected 6 designs that should be safe, sustainable, economical, and proliferation resistant. And molten salt reactors were one of these designs. And we think that this one has really a high potential to bring clean, safe, sustainable nuclear energy. So I first want to show you how nuclear energy is generated today. Today, we are using mostly Generation 2 reactors, which are light water reactors, which means they are using water as a coolant. And to keep this high temperature, the primary loop has to be pressurized. The fuel itself is a solid fuel. It's a ceramic. It's uranium dioxide in the form of small pellets. It relies on the fission of uranium-234 core. And the fuel cycle relies on the fission of uranium-235. So when a neutron hits uranium-235, this one will split into 2 fission products, a few more neutrons, 2 to 3, and will release a lot of energy. And these neutrons can then go on for further fission reaction. Now, the molten salt reactor we would like to build is a really disruptive technology. It's not based on a solid fuel, it's based on a liquid fuel. And this has very interesting properties. With such reactor, because of the molten salt characteristics, you get some inherent passive safety features. You can operate the reactor at low operating pressures. The fuel cycle has a lot of flexibility, and molten salts, just because of their properties, show a good retention for fission products, which is something you, of course, like to have, because in accidental scenario, a concern is always if volatile fission products can come out of a reactor site. So I was mentioning the flexibility of the fuel cycle. In this type of reactor, we can use not only uranium-235, but we can also use plutonium-239, or even a fertile element like thorium. Thorium does not give fission in itself, but after capture of a neutron and a few steps, we get uranium-233 that is fissile, and this can give further fission reaction. Now, when we want to build this technology, we need to very carefully choose the molten salt that will be used as fuel. And this one needs to satisfy some very specific properties. It needs specific neutronic properties, some specific thermal and transport properties. Typically, you want a low viscosity of the salt for the ease of pumping. You want a high thermal conductivity to help the heat transfer. And what I'm working on are the requirements on chemical and thermal properties. We would like a high solubility of the actinide, so that means uranium, plutonium, thorium, such that we can get a lot of energy out of this reactor. These fuels should have a low melting point, so that we can have a lot of flexibility in the operating range while avoiding problems like corrosion. We want a high heat capacity, also for the thermal transfer. And we would like them to have low vapor pressures and high boiling point for safety perspectives. Finally, this salt should be compatible with the structural materials in contact with them. So why is nuclear fuel chemistry so important? Well, I think it's really key to the good performance of nuclear reactors. It will determine the behavior under normal operation, but also the consequences of an accident. And in that sense, studying nuclear fuel chemistry is really at the heart of the progress of Generation 4 technologies and of the molten salt reactor technology. So let's look first at what type of salt you can use in this kind of reactors. Historically, in the United States, for the aircraft reactor experiment and for the molten salt reactor experiment, some fluoride mixtures were used, and you see them here on the slide. They are made of a solvent and a fissile material. Maybe you could think, well, why are you not just using the fissile material? If we would use uranium tetrafluoride alone, this would have a very high melting point. That would not be possible for the reactor operation. So we need a solvent to reduce the melting point of a mixture. Very recently, and also since a few years, there are a lot of molten salt reactor concepts that are coming out in Europe. Since already a few years, a lot of European projects have been dedicated to the study of molten salt reactors, and they are mentioned here, Samofa, Samoseifa, Endurance Mimosa. And more recently, a lot of startup companies propose also a design that they will want to bring to market rapidly. And in these, we have two families of salts that are used, either a fluoride mixture or a chloride mixture. And in any case, we always need a fissile element, we need a solvent, and maybe there is also a fertile element used in the mixture. This is the starting fuel, but once you put it in the reactor, things become more complex. First, you have a fission reaction, and that means that you will be generating during irradiation fission products. You can see these fission products on the periodic table of elements. They have colors, and already you see there are quite a lot of them. They can be soluble in the salt, or they can form metallic precipitates or be gas. And next to these fission products, you also have corrosion products. These accumulate after some time in the salt because this salt is highly corrosive. Typically, the structural materials you can use around the salt are nickel-based alloy, but in these, some elements like chromium are going to dissolve into the salt. So that will mean that these corrosion products will also affect the properties of the molten salt. So you can already see that we have the molten salt fuel with many elements. We add fission products, we add corrosion products. That makes a very complex chemistry. What we would like is to be able to predict performance of these types of reactors already at the design and engineering stage. We want to have models that can predict behavior in regions of temperature, composition, and so on, not available experimentally. And that's because you can never study the entire composition and temperature space experimentally. So you cannot have all the conditions in a laboratory as you will have it in a nuclear reactor. And finally, we would like to have models with very good predictive capabilities for multi-element systems, since once again you have the fuel, you have the fission products, and the corrosion products. Our approach in Delft is to start with experiments. Typically, we will measure the thermodynamics of the system, phase diagram, structure of the salt, and we will couple this with some molecular dynamic simulations, which will give us some more information on structure and other thermophysical properties, such as density, viscosity. Once we have this information, we can build thermodynamic models, as well as density and viscosity models. We do that on the fuel system elements. We add fission products, we add corrosion products, and at some point we end up with a database on multi-component systems. This one allows us to do application calculations. So with our models, we can assess what happens at any condition in normal operation, but also under accidental conditions. Before I dive a bit more into the research we do in Delft, I have to give you a short crash course on phase diagrams. So I'm sure you did not expect that today, so here we are. We use this as a tool in our research. we are plotting the phases table in a system with temperature on the y-axis and fraction on the x-axis. Let's imagine you want to run a molten salt reactor with a mixture that has sodium chloride, basically table salt, although a very, very pure one, and plutonium trichloride. To be able to know at which temperature, which composition you are liquid, you need to do experimental measurements. And this was done in 1959. With that phase diagram information, these experimental points, the blue points, you know that if you are in the red region, you have two solids. That's not good for reactor operation. If you are in the orange region, you have a mixture of a liquid and a solid, also not good for the reactor operation. You need to be in the green region. I have put on the slide the ideal reactor operating window. We want a composition with a low melting point and one where you can operate without going to too high temperatures. Otherwise, you get into corrosion issues. So typically, that would be the operating window. But we cannot run a reactor with just a few experiments. We need to build models. So this is what we do. We build models using the experimental data. We also include the gas in that model, and we know with the model when the gas is stable. So we get information on the margin to boiling. And you can see that if we operate in this window, we have a very large margin to boiling, to the temperature at which gas starts to form. So we can operate the reactor safely in that region. With that introduction, let's dive into molten salt chemistry done in Delft. We are always looking for promising fuel salts. And quite recently, we came across some experimental study done in 1976, long time ago, that was studying the system with sodium chloride, plutonium trichloride, and thorium chloride. We went on to model this system, and we found out that this one is really interesting for reactor operation. And why is that? If you look at the figure, you can see that we have two compositions that we call ternary eutectics that have very low melting points. So that's interesting for reactor operation. And then what do we have in this fuel? We have plutonium. Plutonium is produced in current light water reactors. There are stockpiles of it, also from military sources. So it would be ideal if we could burn this plutonium inside a molten salt reactor. This system also has thorium. Thorium is highly abundant on Earth. It's a fertile element that becomes fissile within the reactor. And then again, it allows us to use a resource that is not used at this moment. And if we make further calculations, we see that this type of fuel has a large flexibility in the choice of fuel composition. We can stay at low operating temperatures while changing a lot the plutonium fraction or the thorium fraction, which means we can also choose the composition based on neutronic requirements or thermal hydraulics requirements. This fuel system, as I mentioned, is interesting. So now we study it as part of a European project called Mimosa. And if we want to get more insight, we need to make these salts. They are not commercially available. And that's a very challenging task because they are highly corrosive, they are radioactive, and they are air sensitive. So we need to work in glove boxes. Recently, we managed to make thorium chloride starting from thorium oxide, and that made us extremely happy, especially because we could get it with very high purity. We measured the sample with X-ray diffraction, and that's a technique that tells you about sample purity. It's a kind of fingerprint. And we saw we had a highly pure product, which is essential because in a reactor you want highly pure salts to make sure you know very well the properties and to avoid corrosion issues. Using a similar method, we went on to make uranium tetrachloride and after reduction, uranium trichloride. And we could even bring these samples to Grenoble at a synchrotron facility where we could do high resolution X-ray diffraction that confirmed really the very high quality purity of these salts. So we can use them to continue our research. In Delft, we cannot work with plutonium. So in that case, we need to find another way. We can use another element in the periodic table, cerium, that is a lanthanide element that shows similar properties to plutonium. So if we want to understand the effect of one fission product, I picked barium in that case, on the salt mixture, we can work with cerium instead. Let's imagine we have a mixture with sodium and plutonium trichloride, and we add barium. We want to know the consequences for the fuel chemistry. So we did some fundamental studies, and I will not go into the detail. You just see that we have a complicated phase diagram, much more complicated than the one we saw before. So we need to do structure studies, calorimetric studies, quenching experiments. But in the end, we get a detailed picture, and we get a model of that system. We can then build a model with three elements: the sodium, the barium, and the cerium. Cerium, you remember, is a surrogate for plutonium. And with that, we can make, again, application calculations. We can estimate what is the safe reactor operating window, which would be the green square on this figure. And what we see is that we can operate the reactor on this green window, but if the temperature would drop down, if we would come into region F, then we get into a region where we have a mixture of a liquid and a solid. This solid has the composition barium-3, cerium-2, Cl12. So with plutonium, it would be barium-3, plutonium-2, Cl12, which means we get plutonium precipitation. That's something we don't want during reactor operation. So it's important to know for the safety assessment. And this is only one fission product, but eventually we want to know what happens with many fission products. So we went on to carry work where we had a starting fuel that was sodium, magnesium, plutonium chloride, and we added a lot of fission products: barium, strontium, cesium, cerium, and neodymium. So we get in the end a picture of the chemistry of the irradiated fuel. With these computations, you can see what happens to temperature versus fraction of fission products. If we remain in the green region, we are liquid, we can safely operate the reactor. But if the temperature would drop down and we get in the red region, we get in a region where we have plutonium precipitation. Again, something we want to avoid. I discuss now precipitation, but there are other safety aspects you want to check during reactor operation. One of them is the change in melting temperature, and the other one is vapor pressure. We can build models, but it's also important to benchmark these models with some experimental studies. In that case, we started with a different fuel mixture, but the idea is the same. We started with a mixture with lithium, thorium, and uranium fluorides, and added now in the lab, experimentally, a lot of fission products to it to simulate irradiated fuel. And then we went on to measure the melting temperature of this mixture against the starting melting temperature. And we saw a lowering of the melting by about 20 degrees. We also studied the vapor pressure of this mixture and looked at retention of fission products. Typically, for the safety assessment, you want to know what happens with cesium or iodine. And this is what we did in this study. So this is all about thermodynamic information, but once we have this, we can also go one step further and model other important properties for the reactor: density and viscosity. Once we have a thermodynamic model, we can couple it to density modeling and also, in a third step, to viscosity modeling. And this is all done with a mathematical formalism called the quasi-chemical formalism in the quadruplet approximation. It's called like this because we used quadruplets, which you can see there on the slide, as the basic unit to describe the liquid. And that is very efficient, but it's still a mathematical description of a liquid. So in our group, we would like to go towards more advanced modeling. And why that? That's because there is a strong link between the structure of the salt and its macroscopic properties. If we take a salt like sodium chloride, that is a strongly ionic liquid. It is basically sodium cations and chlorine anions. But if we add uranium to it, we start to form complexes and a network of polyhedra. In a mixture with beryllium fluoride, you get a polymeric liquid where you form even dimers, trimers, and eventually polymers. This has a direct consequence on the macroscopic properties. If we take the example of viscosity, we can see here in orange the viscosity of a lithium-beryllium fluoride mixture, and you see that this viscosity increases really by 4 orders of magnitude between lithium fluoride and pure beryllium fluoride. So that shows the direct link between structure and viscosity. In the case of the lithium-uranium fluoride mixture, we have an increase with 1 order of magnitude. Still something we need to consider. To study this local structure, we perform experiments at a synchrotron facility. We need to go to a synchrotron because we need a very intense and tunable X-ray beam. We use X-ray absorption spectroscopy, which is the measurement of the X-ray absorption coefficient of a sample. And because we want to measure the liquid, we need to do the experiments at high temperature and in situ. We perform such experiment, we get a figure like this one, which is the absorption coefficient as a function of energy. And regions in this figure, a low energy region called XANES and a high energy region called EXAF. It's the EXAF I'm going to discuss. That's the one we are interested in to know some more about local structure. To perform this kind of experiments, we had to build a setup. We had to design and build a specific measurement cell, which you can see on the picture. This cell is basically 2 boron nitride plates that encapsulate a sample. You can see a small pellet of that sample on the picture in between the plates. Boron nitride is one of the only materials we can use. It's transparent to the X-rays and does not react with the salt. Because we need to heat up the salt so it is liquid, we also designed and built a furnace. And to make sure nothing comes out, since these are radioactive salts, we also have a glove box around it, which we built also ourselves. So when we do these experiments, we go to the synchrotron facility with the cells, with the furnace, with the glove box, everything in the car, and then we get to the synchrotron. And we can start the experiments. You can see on the picture how everything is set up. The X-rays come from the bottom of the picture. They go through the measurement cell and come out. The X-ray intensity is then measured before the sample in the first ionization chamber and after the sample in the second ionization chamber. And with that, we can get the absorption coefficient. I'm going to concentrate on the EXAF region as I mentioned. After some mathematical treatment and some Fourier transform, we get the figures on the right, which we can fit. And when we do this fitting, we get information on the local structure. We can know how many fluorines there are around a thorium atom. In that case, we have, if you imagine you have a thorium in the center, you have fluorine ions around it at a distance of 2.3 angstrom, and on average you have 7 of these fluorines around the thorium. So that gives already some idea of the local structure. But if we want to have even more information, we need to combine the experiments with some molecular dynamics simulations. And we do that in collaboration with someone from Concordia University in Canada. With these simulations, we can simulate our EXAFS data. And if a match is good, and we can work to make sure the match is good, we have been validating the interaction potentials. And once we have this validation, we know we can get a detailed picture of the local structure at any temperature and any composition. And with that, we can know how the so-called chemical speciation looks like. So we can get a picture from the molecular dynamics on the formation of monomers, dimers, trimers, polymers as a function of temperature and as a function of composition. And all of this information we then use for the modeling. You remember, this is the quadruplet you see on the screen. The quadruplet is the widely used methodology to do this thermodynamic modeling, and I say it's very effective. But what we want is to use the structural information to have a more physically representation of the liquid. And to do that, we need the coupling of the experiments, of the molecular dynamics, and in the end, we can have this model of a liquid and the thermodynamics with some more physical basis. We believe that this will have better predictive capabilities using this coupled structural thermodynamic modeling. In the end, we want to gain a fundamental understanding of a local structure, so we can model not only thermodynamics, but also density, viscosity, and thermoconductivity. And this relation between structure and microscopic property, I think, is really key to get this fundamental understanding that is necessary to build predictive models when we will be dealing with multiple elements. You remember the fuel, the fission products, and the corrosion products. So with that, we really hope we can bring the technology readiness level of the molten salt reactor technology towards level 9, which will be the commercialization of this type of reactors. As a final note, I want to mention that this is not my own work, but really the work of a great team. In Delft, I'm really lucky because we have absolutely great technical support, and I'm working with a team of PhDs and postdocs that are highly motivated. And we also have bachelor students, master students that really come to the group, want to do research on molten salt reactors, and are also highly motivated. We also have great collaborations in Europe, with Canada, with people in the United States that all make this research possible. Thank you for your attention.